Welcome back for a dizzying round 2 of the vestibular system. Last time we talked about the fact that one of the important roles of the vestibular system is helping us sense our own position in order to maintain balance. Another important role that the vestibular system has is that it helps us control the muscles that move our eyes, so that in spite of changes to head position, which occur during normal movement, walking, running, etc., the eyes remain stabilized at one point in space. So to demonstrate this, I want you to check out what I'm doing right now. I'm keeping my eyes locked on the webcam while I move my head. You can do it too. Put your finger out here, keep your eyes locked on your finger while you move your head around. You can somehow keep your gaze totally stable on one point, despite the fact that you're moving your head a whole lot, right? So how do we do this? This occurs via a mechanism called the vestibulo-ocular reflex. When you do that activity, it feels like you are keeping your eyes locked in place to fixate on something when you move your head. But in fact, there's no such thing as keeping your eyes locked. Your eyes are attached to muscles. And so in order to move your eyes at all, you need to contract or relax muscles. So to keep your eyes in one place while your head moves, you are tensing and relaxing your eye muscles in exactly the right way to perfectly compensate for the head movement. This should blow your mind. If this doesn't blow your mind, you don't quite get it. Go back and watch it again. Your head moves however it wants to move, and your eye muscles are moving in a way that perfectly compensates for what the head is doing. But it feels like it's happening without any intention or effort. So the way that this works is that the output from the vestibular system about how your head is moving is translated into motor commands for the muscles around your eyes. So how do we know how to perfectly counteract that head movement? You get the head movement as input and the eye movement is the output. Let's see this in action. There's more detail here than you're responsible for. I just want you to see how this process unfolds through each of these steps. So when you turn to the left, there is excitation in the left horizontal semicircular canal. That leads to a cascade of activation in the cranial nerves and its several vestibular nuclei that ultimately leads to muscles on the right side of your eyes being pulled on to make your eyes drift to the right. So as your head moves to the left, your eye muscles tug your eyes to the right to keep them fixated on the same location. So there are cases of people who experience VOR dysfunction and describe it as seeing the world through like a shaky camera lens. One patient described trying to read and being unable to focus on the words on a page because even tiny motions from breathing or small movements would shake his vision so much that he couldn't focus. So he described wedging his head in between slats on the headboard of his bed to keep his head perfectly still so he can read. VOR, man, it's really important. So let's watch one consequence of VOR in action. What's happening? Okay, so the figure skater is spinning to the left for 30 seconds and then she stops. After stopping, what you see is that her eyes slowly drift in one direction and then she saccades, which is quickly moving her eyes in the other direction to correct for it. So your task is to think about why the slow drift of her eyes is occurring. What I would recommend that you do now is pause the video, stare at this, and try to fill in each of the blank spaces with what we learned last time about where the hair cells are going to hyperpolarize and depolarize and what that VOR consequence is going to be. And remember that the eyes drift in the opposite direction of motion. When I turn my head to the left, the eye muscles have to pull to the right to keep gaze fixated on the same spot. So press pause, try it for yourself. All right, so what's happening here, when she begins to rotate left, hair cells in the left ampulla depolarize and in the right ampulla hyperpolarize, and that's going to cause the eyes to drift to the right. When she's been rotating for a while, the endolymph has caught up with the semicircular canals, firing rate of the hair cells returns to baseline, and there's no VOR response. Then when she stops, she's going to have hyperpolarization on the left side, depolarization on the right side, So VOR is going to drag her eyes to the left. Then that quick saccade to the right is to correct for it. So let's now watch that in action. Slow movement to the left, and then a fast saccade back to the right. Now, something that people typically ask at this point is why that fast saccade back to her right happens. So the cause for VOR is clear, but why does that like fast beat back to the right happen? That's occurring because she's trying to look straight ahead. She's trying to look at the camera, focusing on whoever's taking the video. So VOR pulls her eye movements in one direction, and then she voluntarily corrects and to bring them back to center. I mentioned last time that alcohol affects vestibular processing such that being intoxicated makes small head motions feel large. A consequence of this is that small motions lead to large VOR responses. This leads to a behavior called nystagmus, which are jerky and uncontrollable eye movements. Let's watch a video of this. So what's happening here is the person is trying to track a moving object. But when they get to peripheral vision and they're trying to hold still, you see this nystagmus, that little fluttering of eye movements. Even though their body is trying to stay still, small motions from breathing, involuntary movements, etc., are being coded for as much larger motions because of their buoyant cupolas. And so that coding for large motions leads to large eye movements. So nystagmus is occurring when we see these large eye movements that are in response to motion that isn't actually happening. I want to point out, I want to be very clear about this, that if you observe this kind of nystagmus in someone, it's a good indication that that person is intoxicated. But, are you listening? The absence of alcohol-induced nystagmus does not indicate sobriety. The absence of alcohol-induced nystagmus does not indicate sobriety. This is a very conservative test, meaning if someone isn't showing nystagmus, it doesn't mean that they're not drunk. All right, now we're going to move on to talking about how vestibular information is integrated with other senses. And I just want to mention, because it's a common point of confusion, VOR is not an example of multisensory integration. People say, oh, but it's like vestibular stuff and eye stuff, but it's not a form of integration because you're not getting any input from the eyes. VOR is eye movements that happen as a result of vestibular input, but it doesn't require any visual input at all. As you read, the vestibulospinal reflex, or VSR, is another vestibular reflex. The purpose of VOR is to move the eyes to compensate for motion. The purpose of VSR is to move the body to compensate for motion. So keeping our balance is a combination of vestibular input, proprioceptive input, and visual input. You might almost say, no sense is an island. To demonstrate how much visual information works in conjunction with vestibular input, let's call in Violet. Stand on one leg, eyes open, please. Now close your eyes. So we're very used to getting matching input from the vestibular system and the visual system. You're like driving in a car, you're getting vestibular input about motion, and you're getting visual input that you're moving as well. So we use those cues in conjunction with one another. But sometimes we get conflicting input from the vestibular system and the visual system. So if, for instance, you're on a boat and you're below deck, you're in a cabin, it looks like you're just in a regular room. And so as the boat is moving, everything in the room is moving along with you. So that means your visual system is telling you nothing is moving because everything is moving in exactly the same way. But your vestibular system is saying, ooh, right? So you're getting mismatched there. Conversely, if you're in an IMAX or using VR, you might experience a situation called vection or vision-induced perceived motion. So in that case, your body is telling you, your vestibular system is telling you, you are sitting still, you are in your chair. But your visual system is telling you, you are flying over Niagara Falls, or you are running through a VR thing, right? And so you're getting conflicting information from the visual system and the vestibular system. For those of you who have used VR, this can be super disorienting. It can make people feel nauseated, dizzy, and actually become sick. So this is a really interesting question. Why does vestibular and visual mismatch lead us to feel nauseated? We've talked about lots of other forms of multisensory mismatch, right? Like the McGurk effect, you're hearing one thing and you're seeing something else, but that never makes people puke. So what is it about the visual system and the vestibular system being in conflict with one another that can lead to nausea? So one theory relies on the fact that, as you know, the vestibular system is highly sensitive to toxins like alcohol. So in evolutionary history, when we experienced visual and vestibular mismatch, it was likely to be the result of having eaten something weird, of having been inadvertently poisoned. So you eat some weird mushroom, vestibular and your visual systems aren't getting the same input. So best thing to do, get that weird mushroom out of your system, throw it up. So we're in a situation where we have visual vestibular mismatch from like a VR headset, something that evolution wouldn't have predicted, but it leads to the same evolved response. There are huge individual differences in the extent to which people experience discomfort from nausea and vestibular visual mismatch. Right? Some people get really seasick and carsick, other people don't. It's not entirely clear what these differences stem from. The individual differences do tend to be reliable over time. I got seasick when I was a kid. I get seasick now. I'm going to get seasick when I'm old. And it seems to be somewhat heritable. So twin studies show that people who have more shared genetic material tend to be more similar to one another in how they respond to visual and vestibular mismatch. What are the other factors that explain these individual differences? These things may be moderated by experience, like the article you read about ballet dancers. This also seems to be affected by hormones associated with biological sex. So females tend to experience more negative consequences of visual vestibular mismatch than males do. One of the things that's tricky about studying individual differences in vestibulo-visual integration is that the discomfort that it generates may stem from individual differences in how we process vestibular information, in how we process visual information, or in how we combine those two sources of information. It's not clear, it's very understudied. Further research is needed. Now, one of the common ways that we treat seasickness or other kinds of motion sickness is with over-the-counter meds like Dramamine. Dramamine works by acting on a neurotransmitter, acetylcholine, that's very important for vestibular transduction. The Dramamine interferes with synaptic transmission of acetylcholine. It blocks the receptors, and that leads to reduced input from the vestibular system. Dramamine is basically tamping down the vestibular system and saying, hey, enough out of you. As a result, taking Dramamine can make you somewhat clumsy and impair your balance. It also makes you drowsy, which means you're less likely to be moving around and therefore less likely to be getting big input from the vestibular system generated by your own movement. People have made use of the strong connection between the vestibular system and the visual system in perceptually delightful roadside attractions. One of these is called the Mystery Spot. It's located outside Santa Cruz, California, and it bills itself as being a gravitational anomaly. So gravity behaves strangely here. You can stand at angles that seem impossible, water runs uphill, and people become nauseated just by walking around. The claim is that cones of metal with special magnetic properties are responsible. Perhaps they were part of an alien spacecraft that is communicating with other worlds. Perhaps there is swirling magma under the crust that is responsible for this incredible behavior. So that's what they say. But perhaps what's actually happening is that they're making use of visual and vestibular mismatch. So everything at the Mystery Spot is built on a hill and constructed in such a way that your expectations about the relationship between visual information and vestibular information are defied. So all of the structures are built at an angle, like is being shown here in this schematic. So water is subject to the rules of gravity. Humans stand up the way that they normally do. But because we have this perception that houses tend to be flat, we use those visual cues about the walls of the house and the corners and how they come together. And those signals all indicate to us that we are in a normally shaped house at a normal orientation, and it's just the things in it are behaving strangely. I went to the Mystery Spot a few years ago, and I was talking with one of the tour guides, and I was like, oh, hey, I'm a perceptual psychologist. Let's talk about the vestibular system. And he was like, no, swirling magma under the Earth's crust. And I was like, oh, okay, I guess we don't get to talk about perception. All right, I'm going to show you a video that shows how an artist has created a mystery spot of his own.
Behind that glowing hallway is a really cool art exhibit. But don't take my word for it.
This exhibit was totally cool.
And Michael Landy has a PhD.
I'm a professor of psychology and neuroscience at NYU.
Anyway, see for yourself.
What's interesting to me about this piece as a perceptual scientist is that it demonstrates things that I find fascinating about perception. That perception is always an interplay between information that you're getting immediately from your senses and prior knowledge that you use to interpret that information. And when those match, the system works really well.
And when they mismatch, you get a very confusing experience that a lot of people seem to enjoy. When the exhibition was in LA, it drew
somewhere between 17,000 and 25,000, but yeah, a bunch.
That's artist Julian Hober, and his relation to this work?
I made it.
Demon Hill, that's the name of the piece, is inspired by
this stock roadside attraction.
Specifically, gravitational mystery spots, billed as places where gravity doesn't behave normally.
You get nauseated and water runs uphill, and it was totally mind-blowing, and it infuriated me.
Because Julian started to wonder if these spots really were gravitational anomalies.
And all sense of reason said, no, that's absurd.
So he tried making one. And here is Roadside Attraction, translated for the New York art world.
The version that you see in New York reveals the entirety of the trick. It's a room that the interior is completely normal. It's 90-degree angles between the walls, 90-degree angles between the walls and the floors. And then that room is tipped so that it's basically setting on one point. It's a compound angle of about 20 degrees one way and 9 degrees the other way.
What happens when you walk into the room is that the senses you rely on every day to navigate the world
Disagree with one another, and so they fight it out.
I felt seasick.
It is actually kind of disorienting.
Kids freak out. Kids love it, and for me there's a lot of art historical reference, but you don't need any of that to experience the work. It's a very direct and very unsubtle experience.
It hits you at your core, kind of literally. Your vestibular system, your inner ear, is telling you that gravity is one way.
It's the prior knowledge interacting with sensory information from the room
That messes you up. And prior knowledge has a reputation for doing this.
We found that in our own experiments. If you give somebody a collection of lines and they're judging their orientation, you'll fall back on nature. If you walk around the world and take a whole bunch of photographs, and they can be pictures from Manhattan, in which case, obviously, lots of things are vertical and lots of things are horizontal because people build them that way. You go take a walk in the woods, trees are up and horizon lines are down. Animals' legs are vertical. And so that if you take a collection of these measurements of orientations, you'll find the distribution will have a bias towards the cardinal orientations, vertical and horizontal, which means that if I show you an unreliable indication of orientation, you have this prior knowledge that most things you see are vertical and horizontal. So if I show something near vertical, you'll perceive it more vertical than it actually is. So now let's go back to the exhibit. Our prior knowledge that rooms agree with the gravitational vertical is something that is true for us most of our lives. And so when you put yourself in a situation where that's not true, this overwhelming prior evidence takes precedence.
Even when you know that the room is just tipped.
This question about why it's interesting is about revealing how the apparatus works. This is an experience you can't logic your way out of.
A fancy phrase people use is they're cognitively impenetrable. You can know that what you are perceiving is wrong, but you'll still perceive it that way.
You can call it a trick or you can call it an illusion, but it's completely transparent. It's not a trick. It's that depending on the context you're in, your entire experience of the world can be altered, not through fact or fiction, but position.
That is, our experience of the world depends not on what is true, but on what we perceive to be true. On the other hand, Michael Landy says, our perceptual system is usually on the mark.
Is it necessarily subjective? Well, it's inside you. That's kind of the definition of subjective. Is it veridical? Does it reflect what the world really is? Well, most of the time it's pretty close to veridical.
I guess you could see it either way. I'm Flora Lichtman, and this is Christopher Intagliata for Science Friday.
All right, our last stop in the vestibular system is how our expectations may affect vestibular input. So, of course, in order to test top-down effects, we have to give participants some kind of expectation about a stimuli and then see whether their perceptual experience of some phenomenon is affected by those expectations. So in a clever test of this, researchers placed participants in a chair, and the participants were either told that the chair could move or told that it couldn't move. So they got to like feel the motion of it or saw that it was like locked in place. They then made the room totally dark, so it's a pitch black room. And participants were given visual and auditory rotation cues. So if you think about like a space movie where they suddenly jump into warp speed and all the stars are moving past you quickly, yeah, they're getting those kind of like random dot configurations that indicate motion. They're also getting auditory cues that indicate motion that sound like, you know, right? You can tell as it's like tracking in one direction. The participants were then asked if they felt like they were moving. So the question is, are participants going to have this experience of vection? Now, the trick is that the participants never actually moved. The chair remained totally fixed in place throughout the study. The only thing that differed between the two groups was whether or not they thought that they could possibly be moving. And what the researchers found is that participants reported stronger perceived vection. It felt more like they were moving when they were in the condition where they were told that movement was possible. So this shows top-down influences because even in the presence of the same bottom-up input, in terms of the visual and the auditory rotational cues, their expectations about the possibility of movement affected how they felt like they moved. Perception is an inference. So the vestibular system helps us understand how we're moving in space, which helps us to maintain our balance and move our eyes accordingly. It's affected by other sensory systems as well as our expectation. And there's still a ton that we don't know about the vestibular system, in part because there's relatively little research conducted on it. If you go to any major university, they're going to have people who work in the psychology department or the neuroscience department who study the visual system, who study the auditory system. But the vestibular system is very rarely studied. People don't know about it. It isn't taught very often in classes. There's very little scientific funding for it and little appreciation by the public of how important it is. But I hope what you have learned has given you a greater appreciation for what a balancing act it is to know where you are in space. I'll see you in class. All right, so here we are seeing head rotation to the left. So hair cells in the left ampulla will depolarize. You can tell because the stereocilia are bending toward the kinocilia there. If this rotation continued for a long time, the hair cells in the left and the right semicircular canal would return to baseline. And if the rotation suddenly stopped, the hair cells in the right semicircular canal would depolarize. This would lead the person to think they were now turning to the right. All right, so when turning to the left, hair cells on the left side depolarize, those on the right side hyperpolarize, eyes get pulled to the right. When you turn to the right, the situation is exactly the opposite. Hyperpolarization on the left side, depolarization on the right side, VOR response pulls the eyes to the left. All right, so in this roadside sobriety test, what the officers are looking for is presence of alcohol-induced nystagmus. They ask the driver to follow their finger, and if they see those jerky eye movements, it indicates that their vestibular system thinks they are moving more than they are, and those VOR responses correspond to those larger perceived motions. The situation is pretty similar for asking people to walk on a straight line. Because alcohol impairs the vestibular system and gives you that buoyant cupola, now the task of trying to maintain balance is greatly compromised. If you ask people to close their eyes, they're even worse at it because now, in order to maintain balance, rather than having a functioning vestibular system, a functioning proprioceptive system, and a functioning visual system, you're knocking out the visual system and the vestibular system, and people are having to rely solely on proprioception. So they do it less successfully. Isn't this an interesting finding? So the argument is that stronger visual information, clearer visual signals about where you are in space, benefits balance and leads to fewer falls. So this isn't actually a question about the vestibular system. It's a question about visual and vestibular integration. Yep, VOR works in the dark. It happens just the same as it does when you can be getting visual information. You don't need any visual input for VOR to happen. It's not an example of multisensory integration. Why do we get dizzy after drinking alcohol? Because of the differential rate at which alcohol enters the cupola and the endolymph. So one of the things that's happening when you roll down the window is that you're getting somatosensory evidence that movement is occurring. The nausea happens because of visual and vestibular mismatch. Your vestibular system tells you that you're moving, your visual system tells you that you're not. And that's especially true if you are looking in the car so you don't see any movement outside, or you're like reading a book and your whole visual field is stationary. So if you're getting somatosensory cues from the wind, that's another indication that you're moving. So that can help to confirm the fact of motion and alleviate that unpleasant nausea. Rolling down the window also makes it more likely that you'll look out the window and get visual signals about motion from that as well. Okay, let's watch a quick video of spotting so you're familiar with what it is. All right, so the rapid motions associated with spotting means the endolymph in the semicircular canals never get moving at the same rate as the bone. They never catch up. So therefore, when the spin ends, the endolymph doesn't have to lag behind and cause that post-spin dizziness. Here's what I want to end with. How cool is the vestibular system? Don't let it toil in anonymity. Tell somebody something you know about how great this sensory system is and help it get the credit that it deserves. Oh, and don't forget to turn in your problem sets.